Okay, welcome back. Happy Monday, everybody. Today is class number 3. We're going to be talking about limits and continuity today. Hopefully we are working on our 2 projects, arbitration and trucks. Folks who have been following the recommended calendar have observed that the trucks project is much more straightforward than the arbitration project. This is true. In fact, in a very real sense, the arbitration project, the one about the mountains and the beach, is the hardest of the 6 projects that you're going to do this semester. So why is it the first one I handed out? Well, in terms of the calculus, it's the easiest of the 6 projects. And so the thing that makes the Mountains Beach project hard is all of the reading and all of the new social science concepts that are introduced in the reading. Once you get to the actual math, I'm hoping that we find it is actually not going to be all that hard, but it is a slog in getting through that reading. Follow the recommended calendar. You'll have some time to digest. You might need to read some of the stuff twice. I know I did when I read that project for the first time. It was brand new to me as well. But just follow the recommended calendar and you should be all set. Okay, a couple of logistical things before we jump in. So first of all, everybody grab a green bookmark. They're on your tables. This is the schedule for when math faculty will be on duty in the math studio. You're welcome to go there anytime the building is open, but this is when you will find somebody in there to answer your math questions, all right? So, and if it's convenient for you, take a photograph of that instead of the bookmark. The other handout for today is here. It says homework as assessment on the top, so everybody grab one of those. Homework as assessment, it's just a 1-page reading. Everybody have these? Yeah. Okay, so the homework as assessment reading is an idea that the author has about changing the perspective that a lot of folks have on their math homework. Many of us experience a disconnect between doing math homework at home and then doing well on tests in class. And that disconnect is a problem if you're not doing well on the tests in class, but you feel like you're doing all the homework, and how do we bridge that gap? So this is one idea for bridging that gap. The idea resonates with me. I wish I would have had this idea presented to me when I was a student myself. Hopefully it will resonate with some of you. I don't know that I'm really going to talk about this thing again, but it's short enough that it's worth a read. And some of you might say, no way I'm going to do that. That's going to take way too much time. But some of you might feel like, hey, that's worth a try. So give it a shot. Remember, the point of doing math homework isn't to like get a 4 out of 4 on my little page here where I'm counting scores on your math homework. It's to understand the material. And the ideas presented in this paper have the goal of helping you better understand the material. That said, the description in the paper is going to add time to you spending on math homework. So if that is not a possibility, then I might say do less math homework, but spend more time on it according to the ideas in this paper. And don't worry about getting a 4 out of 4. The homework is worth a very tiny part of your grade anyway. It's much more important to understand the concepts than to get that 4 out of 4. Speaking of homework, last fall when I last taught this course, the number of homework problems was much greater in each section than it is right now. I was getting a very clear sense from my students that there was too much in the workload for this class with studying for quizzes and tests, doing the projects, doing the homework, doing the reading. All of that was just adding up to too great a commitment for a 4-credit class. So Caitlin, my colleague, and I cut the homework down for this semester. Sometimes we cut 1/3 of the problems off. Sometimes we cut the problems in half. That is to say, it is like a bare minimum assignment as far as we are concerned right now. It might not be enough for some of you for some of the concepts. So if you feel like you need more practice, even though you finished the homework, there's plenty more problems in that textbook that we did not assign, okay? So you know how you are doing on this material. Do more if you're not feeling comfortable at the end of the assignment, okay? All right, so let us jump in on page 19. We'll start here at the top. In this class, we calculate limits, and we discuss the concept of continuity. Limits are at the heart of finding slopes of tangent lines, which is a fundamental process in Calculus 1. So last class, we talked about our zombies running a race, and we talked about tossing a ball off of a tower. And in both cases, it turned out that the slope of a tangent line was the instantaneous velocity at that one particular moment in time. So finding slopes of tangent lines is important for velocities, and it's important in a lot of other contexts that will come up as well. And we got to get this idea of limits under our belt in order to talk about slopes of tangent lines. So let's take a look in the demo. Let's find the value of this limit. This is a limit as x approaches 0 of x over the square root of x plus 1 minus 1. Ultimately, we want to know what is this number equal to. And what that means is that if we plug in numbers for x really close to 0, that's the x going to 0 part with the arrow, what does this fraction approach? The very first time I see a brand new limit, I just plug x in. Just plug it in. What do you get when you plug 0 in on the top? 0. And on the bottom? It's also 0, square root of 1 minus 1. So it appears that when we plug x equals 0 in, we get, where is it? 0 in both numerator and denominator. That is important enough. It's got a name. It's called an indeterminate form. Looks like it goes to 0 over 0. Undefined is, I guess, an okay answer for some limit problems, but not this one. Just because we have a 0 in the bottom doesn't mean you right away just get to jump to the word undefined. 0 divided by 0 means we've got some more work to do. We're going to do some algebra, but first, let's take a look at a picture. So this is the same function that was up above, x over square root of x plus 1 minus 1. Here's the window. It's negative 5 to 5 and 0 to 5. And those hash marks are the scales. They're all ones. And so if I think about this graph, as I approach x equals 0, so I'm going to pick numbers on the x-axis, and I'm going to trace them on the curve. So like if I pick x equals, I don't know, like 4, then I'm up here at some y value. Or I could pick x equals 2, and I'm over here at some other y value, and I'm just tracing all of these guys in, and I'm tracing that curve, and it appears that the y values are honing in on that point right there. Yeah? Just looking at hash marks, what does it look like that point is? Looks like 2. Probably you can look at it better on your picture than mine by this point. So it looks like 2. It turns out it's not enough to just look from one side. On today's activity, at some point, you'll start looking from both sides of the number, 0 in this case. And so we plug in some negative guys, but again, approaching 0 on the x-axis. And again, we approach that same circled purple point. It looks like it's 2. So it appears, and we'll just write our here, limit. So go ahead and copy this just for practice with the notation. So limit as x approaches 0, copy the whole function. It appears that the answer is 2. Now, if we were to zoom in on the graph, do you know what we would see at that purple circle there? We'd see a hole, because we've already established you cannot plug 0 in for x. When you plug 0 in for x, you get 0 divided by 0, which most certainly is not the number 2. So it is a hole there. But it turns out that if you just move a tiny bit to the right or left of that hole, you're at like 2.001 or 1.999. It's really well behaved near the hole. It's just at the hole. It's just this one moment where the graph blinks out of existence. So when I say equals 2, some of you might argue and say, well, it's not really 2, right? It's like 2.01 or 1.99, but I mean, really, like it's equal to 2. The haziness in this problem is captured in that limit notation. When I say limit, I mean we can get really, really close to 2 by picking numbers really close to x equals 0 in this case. So equals 2. Okay, another way to think about finding the same limit is to look at a table of values, which TI 8384 can do no problem. So again, here's the same function, y equals. Inside of table setup, I can tell you where this exists if you want. We're going to start our table. Actually, the table start is not relevant. If you change the independent variable from automatic to ask, then you get to type in whatever x's you want. And I have typed in a very specific collection of x's. Negative 0.1, negative 0.01, negative 0.001, all getting closer to x equals what number? The x values, what are they getting closer to? 0, that is what I'm after, and 1.9487 and 1.995 and 1.9995, and it sure feels like they're heading to 2. What happened when I got greedy and tried to plug 0 in directly? Error, you can't plug 0 in, not even something as smart as our calculator can plug 0 in. But again, it's not enough to just go from one side of x equals 0, but go from the other side as well. 0.1, 0.01, 0.01, 001, 2.0488, 2.005, 2.0005. What does it appear the y values are approaching? 2. And so it's more evidence, not proof, but it's more evidence that 2 is the right answer. One small detail, if you have one of these particular calculators and you highlight one of these numbers, you'll see it's rounding in the table, but you can get a lot more digits if you want more digits. It's at the bottom. Okay, and then finally, let's do some algebra and really convince ourselves beyond a shadow of a doubt that it's 2. You can look at the picture and say, it looks like 2. You look at the table of values, it looks like 2. But the way to really see that it's 2 and not, 2 point and then 17 zeros followed by a 4 is to do some algebra. So here's the algebra. Go ahead and write this part. So x, I'm copying the original. Okay, so we're starting with that fraction, and we are going to manipulate it. We're going to write it in another form. And what we're going to do is a technique called rationalizing the denominator, probably something you've done before. You guys remember what we're supposed to multiply the bottom of this thing by to get rid of the radical? One minus root x plus 1. Does that sound right? So I think that's close. I don't think that's quite it. Is it over here? Square root of x plus 1 plus 1. That's it. You copy everything, but you change that one operation in the middle. It was a subtract. We'll make it add. If it had been addition, we would make it subtraction. But you can't go around doing that to the bottom of a fraction without immediately doing the same thing to the top. Okay, and so now we're going to do some algebra here. On the top, I'm actually just going to copy it with parentheses here. Turns out distributing is heading us the wrong way, so leave that as it is. But we are going to distribute on the bottom. I'll put parentheses in just so we're really clear. This is a big distributive thing on the bottom, right? Foil or lobster claw, however you think about distributing. Okay, and lots of good things are going to happen, so here we go. Yeah, so what do you get when you do the first times the first? It's just x plus 1, right? The radicals cancel each other. All right, that's good, x plus 1. When you do the outers, you get plus radical x plus 1, right? Put that plus radical x plus 1. And when we do the inners, minus radical x plus 1. Hey, look at that. And then finally the lasts, minus 1. Okay, so that's what you get when you distribute. Yeah, but then lots of things cancel. This is why multiplying by that was the right thing. Square root of x plus 1 minus this, I miscopied something. Square root of x plus 1 minus the square root of x plus 1, those cancel. And then as a bonus, the 1 and the minus 1 also cancel. So we're just left with x on the bottom. And now that x cancels the x that's been hanging out in the front. This is why I didn't distribute before. I want that x to be there so I can cancel it right now. So we cross those guys off, and we're just left with this thing in the parentheses. So then I'm going to rewrite my limit. This is an x going to 0. That was part of the original problem. And all we have is the thing in the parentheses, square root x plus 1 plus 1. And from our perspective, this is a brand new limit that we have not analyzed yet. And as I said earlier, every time I see a brand new limit, I just plug in. I'm a greedy guy. I would love to just get rid of the graph, get rid of the table, and just be able to plug in. When we plugged in originally, what weird thing did we get? 0 over 0. I don't know what to do with that. But when you plug in 0 now, you don't get anything weird at all. You get a perfectly good number, and that number is our answer. So we're just plugging in 0 for the x. 2. So we made a good guess based on the graph. We made a good guess based on the table. This is how we do it for real. Any questions on that? And so for today, this is just going to be like a mathematical game that we're playing where it's just like random limits that the teacher said, hey, go, analyze these things. But really, the limits that we're going to be interested in this semester are going to have to do with slopes of tangent lines. And so we'll make that connection later this week. Okay, so on the next page, let me pause for just 1 second here. So very soon in this class, we're going to spend, I don't know, 10 minutes talking about that arbitration project. Not today. I don't know if it's Wednesday or Friday. I think it's Wednesday. So if you could get on track with that recommended calendar for the arbitration project before Wednesday or Friday, whenever we're going to talk about it together, that would make it more meaningful the 10 minutes that we spend together talking about that arbitration project. All right, so can I get a show of hands? Raise your hand if you either have a graphing calculator on you or on your cell phone. So that's a bunch. Yeah, that's probably enough. So if you don't happen to have one, the very first part here says investigate by looking at a graph. You'll look at the graph of your neighbors. While you guys are working, I'll just put a couple of graphs up here on the screen in case you don't have the graphing calculator, but really just check in with your neighbors. And this activity is quite robust, so you're going to be working solid to try to get through it all. Let's give it a shot.